Have you ever wondered if we could literally read the electrical language of the human body? Well, in today's explainer, we're doing exactly that for the visual system. We're demystifying ocular electrophysiology. We're going to explore the absolutely fascinating field of measuring the electrical signals generated by the eye and the brain, and see how it bridges the gap between anatomy and function.
Picture this. It's a classic medical detective problem. How do you test the vision of someone who simply cannot read an eye chart? Think about it. What if your patient is a tiny infant, someone who is nonverbal, or someone with a complex condition who just can't cooperate with a standard vision test? You can't exactly ask them, hey, which is better, lens 1 or lens 2, right? You need a completely objective way to see exactly what their visual system is doing.
Okay, let's dive into this. Here is our roadmap. First, we'll compare structure and function. Next, we decode the retina. Then, we trace the visual pathway. And finally, we wrap up by diagnosing hidden eye diseases. Starting with Section 1, structure versus function, or as I like to think of it, the hardware versus software analogy. So, to really wrap our heads around electrophysiology, let's just think of the eye like a digital camera. When a doctor does a standard clinical exam or uses structural imaging, they're basically checking the hardware, the physical camera body, just making sure nothing is visibly broken. But electrophysiology? That's a totally different ballgame. That is testing the software and the electronic sensors. It measures the functional electrical responses, telling us not just what the eye looks like, but how well the retinal cells and visual pathways are actually firing when light hits them.
Moving right along to Section 2, let's decode the retina by looking at the electroretinogram, or ERG for short. Now, what's really interesting here is that the ERG is our ultimate objective tool for the front of the visual system. When light hits the retina, your photoreceptors and neurons spark with tiny electrical signals. By simply placing surface electrodes, we can pick up on these signals and map them out into characteristic waveforms. The best part? The patient doesn't have to say a single word. The ERG just records the retina's raw electrical reaction to the light. And these electrical sparks create very specific waves on a monitor. First up, we see the A wave. Right after a flash of light, the photoreceptors actually flip their electrical charge, a process called hyperpolarization, which creates this initial negative dip. Because this comes mainly from rod and cone photoreceptors, if there's an issue here, it points straight to outer retinal dysfunction. After that, the signal travels deeper inward, generating the B wave. This is a much larger, positive wave that comes mostly from the inner retina's bipolar and Mueller cells. It's literally a real-time map of the signal moving through the layers of the retina. And doctors have an entire toolkit to manipulate this process, which is wild. By controlling the light, they can isolate very specific cells. For instance, testing a dark-adapted eye, a scotopic test, lets the rods take over, letting us investigate night blindness. Need to test central and color vision? You use a light-adapted photopic test for the cones. And since rods just can't keep up with rapid flashes of light, a high-frequency flicker test singles out cone activity perfectly. We can even use checkerboard patterns to check the macula, or a multifocal ERG to map out function across the whole back of the eye. It's like having a magnifying glass for individual microscopic cells. All right, on to Section 3, let's trace the visual pathway with visual evoked potentials. Because let's remember, vision doesn't just happen in the eye, it ultimately happens in the brain. While the ERG checks the retina, the VEP checks the integrity of the entire visual cable. We're talking the whole journey, starting at the retina, traveling down the optic nerve, crossing over at the optic chiasm, moving through the optic tracts and radiations, and finally hitting the visual cortex at the very back of your brain. The VEP measures that exact incredible spatial journey. To actually record this, we just place electrodes right on the scalp, directly over the occipital cortex, which is the brain's visual processing center. Then we show the patient visual stimuli, like an alternating checkerboard or diffuse flashes of light. Those flashing lights are absolutely crucial for very young kids or anyone with poor vision who just can't focus on a pattern. The wave we get back shows us exactly how well that signal traveled through the entire visual system. Now here's where it gets really precise. The most important part of a pattern reversal VEP is a waveform called the P100. Why exactly 100? Because in a healthy, normally functioning visual system, this positive wave hits the visual cortex in exactly 100 milliseconds. So the crucial point here is that timing is absolutely everything. The P100 is highly reproducible, and its arrival time, its latency, is super stable. If that signal takes even a fraction longer than 100 milliseconds to arrive, we know there's a conduction roadblock. A delayed P100 is basically a medical smoking gun.
It almost always points straight to optic nerve dysfunction. Which brings us to our final section, diagnosing hidden eye diseases and solving these medical mysteries. So, how does this actually look in the clinic? Well, imagine a patient comes in with unexplained vision loss. A doctor looks at their eye, and structurally, the optic disc looks totally normal. The hardware seems fine, right? But then they run a VEP and see severely delayed conduction. And this brilliantly illustrates how electrophysiology can spot conditions like optic neuritis or demyelinating diseases that a standard physical exam would completely miss. This same detective work applies to inherited retinal diseases too. Take retinitis pigmentosa, for example. In this condition, the rods usually start failing first. By using a scotic ERG, doctors can actually measure that drop in electrical activity long before any physical damage is visible to the naked eye. The cones might eventually be affected as the disease progresses, but the ERG acts as this incredible early warning system. And frankly, this objective data is a total game changer, especially in pediatric ophthalmology. Think about a baby with a congenital retinal issue. They can't exactly tell you that the world looks blurry. A regular exam can only tell us so much, but electrophysiology gives us hard, undeniable data. Plus, in adults, it helps doctors tell the difference between organic disease and non-organic vision loss. If someone says they can't see but their ERG and VEP are completely normal, we know for a fact that the physical pathways are perfectly intact. Let's move beyond just diagnosis, though, and see how this builds into the future of medicine. Modern electrophysiology is evolving right alongside molecular genetics. As things like gene therapies, neuroprotective treatments, and even retinal implants become reality, we need to know if they're actually working. We use these objective tests to monitor those precision treatments over time. It's essentially the measuring stick for next-generation cures. By combining what we see structurally with these functional electrical tests, we're finally getting the full picture of visual health. So as we keep mapping out the electrical secrets of the eye and combining that with cutting-edge genetics, could the end of incurable blindness be just a signal away? It's an absolutely thrilling frontier in science. Keep that in mind the next time you open your eyes and take in the world around you. Thanks for joining me for this explainer.